Right. So good afternoon. Can you see the slide that is time response for the system model? Is it visible?
Yes, ma'am.
Okay. There. Turning up. Okay. So today what we are going to do is we are going to study the time response for a system model. Now this actually would be covering a lot of things which you are already familiar with in your second years in signals and systems class. You were supposed to be taught some of these. So first of all, we'll be studying some general things about the responses, and then specifically for the first order and second order system we'll be trying to see the specifications, etc. So many of it will be common, but here we would like to gain a better sort of understanding regarding each of these. In case you are familiar with the terms as well, maybe we can read a bit more into what is happening by what we are going to do today. So right now I'll start with this. Right. So over here, you see that the time response for the system model consists of two parts, basically. It's a summation of two responses. One is the natural response and the other is known as the forced response. Right. So the first one, as you can see, is known as the natural response, and the other is known as the forced response. I'll go into the details of this. In case you are unable to understand at any point, please let me know, because I've got a sore throat today. Maybe sometimes I might become soft or anything. So please let me know in case you cannot hear or cannot understand, my words are becoming jumbled and so on. Right. So first of all, what are these? That is the natural response and the forced response. That is what we are going to see. So disturbance. Okay. Right. So basically, first we come to what the natural response of a system is. Right. So I'll read through the slide first, and then I'll be explaining. So over here you see the form or nature of this response, that is the natural response, is dependent only upon the system and not on the input. Right. So what do I mean when I say that? I mean that basically, if we apply the same input to different systems, we are going to get different responses. For example, for example, if we have a first order system, you are familiar with this response, right? So first order system, say a general transfer function is what we are looking at, k by s plus a or something like that. So, oh God, people are keeping on turning up late. Okay. So basically, if a step input is applied to a first order system, an exponentially rising response like this one is what we are going to get if the system is, of course, stable, meaning that it has no right half poles, only left half pole, one pole actually, because it's a first order system. The pole is in the left half of the S plane. So this would be the response. Of course, you can verify the response given a system. You know how to do that, isn't it? So if I apply a particular input, you have to take the Laplace transform of the input, and then you have your transfer function with you. So Cs by Rs, meaning the output by input, is equal to the transfer function, right? So the output will be equal to, that is Cs will be equal to Gs into Rs. I'm saying these verbally in case you're unable to understand, please let me know. So Cs will be equal to Gs into Rs, and then you know Gs, that is the transfer function, you know the input which is applied. In this case, I'm speaking of a step response, step input, for example. So you can multiply Gs with Rs, and then if you want to get Ct, that is the time response, what you do is you have to take the Laplace inverse of the right hand side. So in doing that, you will get an expression, and when you plot that on a graph paper, you're going to get some sort of curve or response. So this is basically for a first order system, if the system is, of course, stable. However, if the same step is applied to a second order underdamped system, you are familiar with this, that's why I'm directly telling this. So underdamped means what? It's going to have a response which looks like this. It is a decaying sinusoid, and it will be like this. So what I want to say is that the response of a system depends on the system itself. Even if the same input is applied to, say, system 1 and system 2, the responses are going to be different. Why? Because of the natural response. So the form of the natural response is dependent only upon the system. So applying the same input to different systems will give you different natural responses. Now, the natural response, physically, what is it? It describes the way in which the system dissipates or acquires energy. So, I mean, if I say that this response, the second order response is like this, you can say that it is basically there is increase and decrease and increase and decrease, finally going to a steady state value. So, it describes the way in which the system will be dissipating or acquiring energy, right? So, the natural response is one of the responses which are constituents of the output response of the system, right? What is the other response that we speak about? The other sort of response is known as the forced response. Now, forced response is the form or nature of this response is dependent upon the input, meaning that for the same system, say for example, we have a second order system like this, an underdamped system, just for example. Okay, so now if I apply a step input, my response will be like this. If to the same system I apply a ramp input, the response is going to be different. It's going to be, say, like this, right? So it means that this, I mean, is because we have the response depending not only on the system itself, the characteristics of the system itself, but we also have the response depending on the nature of the input which is being applied. So that is known as the forced response, meaning the form or nature of the that portion of the response which depends upon the input is known as the forced response, right? So as I said, to sum it up, for the same system, if you apply different inputs, responses are going to look different, right? Of course, the overall response, say for example over here, if I apply step input to a second order underdamped system, the response is going to be like this. So if it is a step, only then this response is going to be like this. Also, if the transfer function is, I mean, a second order with a slightly underdamped sort of characteristic, only then this will be valid. If either or, meaning if either the system changes or the nature of the input changes, the response will be different. Right. Now, again, coming to a definition which you are familiar with, I mean, definition you are, yes, basically familiar with, but we are going to, sorry, we are going to read a bit more into it. So, the term is known as the poles of a transfer function, right? So, what are poles of the transfer function? We find that the poles of the transfer function are those values of the Laplace transform variable s that cause the transfer function to become infinite. So over here on the right hand side, we have an example 5 by s plus 5 is a transfer function, right? So over here, how many poles are there? You can see that there is one pole at minus 5, right? So why do we say that? Because at s equal to minus 5, what happens? The denominator becomes 0, and it means that the transfer function overall becomes infinite. So that is why minus 5 is a pole of this system. So of course, inherently, I mean, sort of intuitively, you are familiar with this. You know, I mean, if you look at a transfer function, what are the poles? You can say that from your knowledge of the second years. But actually, this is how it is defined, one of the definitions. There is, however, I mean, this first portion is not a complete definition. There is a second part to it as well. So the next slide says that. So yes, I mean, the value of the when the value of the Laplace transform variable s makes the system overall transfer function become infinite, that is defined, that value is known as the pole of a transfer function. That's understood. There is, as I said, another, I mean, case where we may be having poles of a transfer function. So what are those? So any roots of the denominator that are common to the roots of the numerator of the transfer function are also called poles of a transfer function. Now I'll try to explain that with the help of an example. You find a transfer function written on the right hand side. So here you find you have the 5 by s plus 5 intact as we had in the previous slide. Also along with that, we have another pole at another 0, right? And what is a sort of what do you notice about the pole and the zero? You find that the pole is almost at -1, just at -1 point triple not 1, and the zero is almost at again -1. It's actually exactly equal to 0.999. So now the question is that, say, for example, if you are using some sort of calculation or computation, is it necessary to consider both these, that is the pole and the zero, which are very, very closely located? Is it essential to consider these explicitly when we are dealing with this transfer function or not? That is the question. What I mean to say is that, yes, you can see that there is 1 0 and 2 poles over here, fine. But now, I mean, the question is, as I said, the question is whether it is essential to note the effects of all these poles and zeros, or whether some sort of pole zero cancellation can help us in the way that we can simplify the system dynamics. There is a lot to be gained if we can simplify the system dynamics. Say, for example, if you have a 25th order system and you can, I mean, sort of cancel out some of the poles and zeros and then make it into a, say, fourth order or third order system, then naturally you have a lot to gain from that, because you can analyze by using very simple methods and lots of computation is not required, etc. So simplification is to our advantage, to the advantage of control systems engineers, if of course cancellation can be done. Now the question is whether such cancellation can be done, meaning that if I say that, okay, I'm using a sort of computer or a calculator where cannot, I mean, sort of go beyond, say, one place of decimal accuracy or two place after decimal accuracy, something like that. So what will happen? The denominator will be approximated as 1.0, and the numerator also will be, denominator means this pole location is what I mean. It will be um, it will be approximated as minus 1.0, and the zero location also will be approximated as minus 1.0. So that means now this s plus 1 by s plus 1 can cancel out. Now, should I cancel them out or should I not cancel them out, right? So whether I should or whether I am permitted to, or whether it is feasible to cancel out such poles and zeros will depend upon some very important considerations. Now, if there, I mean, the pole and the zero, which I want to cancel out, if both of them are in the left half of the S-plane, meaning both the values are negative, which is the case over here. You can see this is a left half zero, this is a left half pole, right? I hope you understand what I mean. I'm sure you understand rather, because you have done your signals and systems over there. You know what I mean by the left half of the S-plane. So since both these are to the left half of the S-plane, that is why both of these are actually, it's a stable pole and a stable zero, which I really want to cancel out. So such cancellation is actually permissible. On the other hand, if I had this, say for example over here, if I had s minus 1.0001, and over here I had in the numerator s minus 0.999, right? So again, I mean, numerically that 0.999 can be approximated as 1.0, and the denominator as well, you can I mean, approximate it as minus as 1.0, right? So now, I mean, I have the transfer function as 5 into s minus 1.0 by s plus 5 into s minus 1.0. Now, should I cancel out, or I mean, is it correct to cancel out the pole with the corresponding zero? The answer is no. You cannot cancel out unstable poles with zeros, because now, I mean, it is absurd to assume that both these are located exactly at the same place. Same place means that in the S plane, if they are coincidental, then you could have cancelled it out. Now, if they lie in the left half of the S plane, well, they do not pose a problem to the stability, and it is sort of permissible to cancel them out. On the other hand, if they are in the right half of the S plane, it means that even minor sort of, I mean, deviation in between the two values would mean that you have a one unstable pole correspondingly being, you can say, unknowingly being cancelled out by a right half 0. So in that case, though the system will actually have an unstable nature, you will be under the false impression that it is a stable system because you have cancelled out an unstable pole with a right half 0, right? So in such cases, cancellation is not permissible. However, what we try to say over here as far as the definition is concerned is that any roots of the denominator there are which are actually cancelled out by corresponding roots of the numerator as well are called are called the poles of the system, right? The usual symbol that is used for poles is a cross. You are familiar with that, I'm sure. Next, we come to the concept of zeros. So over here again, those values of the Laplace transform variable s that cause the transfer function to become 0 will be called zeros. So over here, say for example, s equal to -1, you have this as being equal to 0, and consequently the overall transfer function will be equal to 0. So that value, that is s equal to -1, is 0 for this transfer function, right? Also here as well we have the concept of cancellation of poles and zeros. So any cancelled zero, meaning any zero which was already there but has been cancelled by a pole, are also going to be called as zeros of the system. As I said, whether such cancellation is permissible or not is a big issue, and you have to keep in mind, you have to look at it and see whether it is, causing an unstable pole to be cancelled by a corresponding zero. If that is the case, even though you have apparently the pole and the zero location are exactly the same, you think it is exactly the same, even then you should not cancel it out. Because now can you tell me something, this, say for example, here I have s plus 1.0001. Now this value over here, or for that matter this s plus 5, so where does where do these values come from as far as the physical system is concerned? Physical system, from the physical system, how do we get such values? How do we get any value of whatever is there in the transfer function? Can you tell me from which portion of the system does, this value or that value come? How do we get the transfer function in the first place? We have a system, we write down the equation for its dynamics in terms of a differential equation. Then what do? We take the Laplace transform, and then of course we try to write it in terms of output by input, Laplace transform of output by Laplace transform of input, by setting the initial conditions equal to 0. So that is how a transfer function is obtained. So now can you tell me how, say for example, this s plus 5, how does this value 5 come? 5 means I don't want to, how this exact value comes. So what I mean is that how does, any pole location or zero location come physically from the transfer from the system? Say for example, you have an RLC series circuit. So over there now, if I ask you to find the transfer function, etc. Now, I mean, after you get the transfer function, from where would the values of the pole and zero locations come?
Ma'am, by solving the characteristic equations.
That is okay. Now, what I mean to say is this numerical value over here, from which, I mean, in the physical system, you have, say, for example, as I said, RLC circuit, right? So,
RLC, if we have, then it can be any means under them or that situation, and we can then quadratic equation, we can split up the roots. Then.
fine. So, in the root
time
location, what? Yes,
constants of the system. Time constants of the system.
time constant of the system. You are saying, where does the time constant come from in the first place? Time constant or damping ratio or anything, whatever you are calculating, it comes from where? If I have
Their poles.
now poles you are obtaining. Physical, if you have a system where you have a source of voltage, a resistance and
When the
inductance.
when the signal reaches a specific percentage percentage of the steady state value 1 by percent 1 by times the steady state value, then that
Hmm,
time
that
is
is
time
okay.
constant.
That is the, yes, of course, that's the definition. But I mean, how much will be that time constant? What, I mean, in the system defines that?
Speed.
Speed. Okay, speed. Now, I mean, how much will be the speed? How is that defined? I mean, we are going away from the actual answer. What I'm trying to say is that, say, if you have, as I said, RLC. Now, if that's going to
From the value of R, L, and C.
very good, isn't it? It's going to come from the parameters of the system, whatever be your system. So in RLC circuit, R, L, and C will be, I mean, say if, for example, it's equal to root over of LC or whatever, I mean, is going to give you this value or something like that, right? So depending on what your how it's connected, etc., etc. But it's going to come, these numerical values are going to come from the parameters of the system. By parameters, I mean, for example, in the electrical circuit, it could be resistance, it could be inductance, it could be a combination of those, etc. In your mechanical system, it would be mass or spring constant or whatever, I mean, friction or whatever it is. So basically the parameters of the system are the things from where the locations are computed. Okay, so now, I mean, if I say, okay, after a lot of calculation, etc., etc., I've got this value over here in the denominator and I've also got this value in the numerator. So what are the chances that these are numerically exactly the same? Practically, I mean, the probability is practically, I mean, very close to zero, isn't it? Because it's being calculated from the value of, say, for example, the resistance and the inductance. Now, if I say, okay, I have a 5.75 ohms resistor, what are the chances that the resistance value is exactly that? I mean, almost none, because I mean, there would be, say, for example, heating effect could be there, the impurity could be there. When it's being manufactured, it's, I mean, sort of, it could be having it's going to have a value close to whatever I specify, but not exactly the same, right? So basically, and it could be having, say, instead of 5.75, it could be a 5.752. So I mean, who knows? So what will happen is that the parameters which are dictating these numerical values, apparently I'll see that, okay, I can cancel these out. But I mean, if I assume that because I see that it's s plus 1 in the numerator and s plus 1 in the denominator, and I can cancel it out, I should somehow, I mean, first of all, think whether such cancellation is permissible. Permissible means if it is a left half pole and that being cancelled by a left half zero, then because there is no problem about no issue about stability, I can try to cancel it out, knowing very well that they are not coincidental. Not coincidental meaning that though they apparently are located at the same, I mean, location, in practice there is a slight amount of difference, however small they, I mean, however small the difference is. On the other hand, because of that reason, if they are in the right half, meaning that it's right half zero, that's an unstable, sorry, yes, an unstable pole is being cancelled by a right half zero. In such a case, because of the fact that numerically they are never going to be exactly the same, even if, I mean, they are numerically exactly the same, a slight sort of ambient change in the ambient condition may make it have a different, slightly different value, and that means that apparently, I mean, the system will look stable if I cancel out such poles and zeros, but actually it's an unstable system, which, I mean, the dynamics has been suppressed. I will not be able to know about the dynamics because I have made an improper or a wrong cancellation at some stage or the other. So that is why you have to be very careful when you are doing, I mean, such cancellations. You should never cancel out right half poles with corresponding zeros. However, in the, if they are, both of them are in the left half of the spline, you may, if you think that they are close enough, you can cancel it out to simplify systems. You can actually take different systems and uh, try to verify that as well. Is anybody saying something? So now, we come to a first order system. Now over here, we have a specific first order system which is given as the transfer function of which is given over here as s plus 2. I don't think anybody, okay, no problem. Okay, so the transfer function is given as s plus 2 by s plus 5, right? So the input is, you can see a step input where the Laplace transform is given by 1 by s, and this is the response which is coming out, right? So now, first of all, the mapping of the pole and the zero has been done. So here you see the pole is located at -5. This is S plane, of course, real axis and imaginary axis, right? So S equal to, I mean, -5 is the location of the pole, and S equal to -2 is the location of the zero. This much, of course, you are, I mean, you already know. On the other hand, now, okay, so as far as the input is concerned, input also separately can be plotted on a separate plot, not the same plot, of course. I mean, it's a different, input means input domain is different. So basically, if I try to again, I mean, put it on the, I mean, real versus imaginary, if I choose the axis like that, I can plot it somewhere. So over here, because I mean, R is equal to 1 by S, I've put the input pole, as it is called, within quotation marks, I would say. It's not the pole of the system, mind you, but it can be plotted at the origin like this one, right? So now, okay. So now the same system we are continuing with, right? And this is the pole zero plot only, meaning the location of the zero and the location of the pole has been shown, and the same input pole has been shown over here. Now, if I were to obtain the response for the system to a step input of unit amplitude, so unit amplitude means the RS is equal to 1 by S, right? And the transfer function, of course, is given over here. So what is CS? CS is equal to GS into RS. So GS is S plus 2 by S plus 5. You can see that over there. RS is equal to 1 by S. So overall, CS is equal to this, right? So now the next step, of course, you are aware of it. I have to break it up into partial fractions, right? So after some minor calculations, it happens to be that this particular, this particular expression can be broken up into 2 by 5 by S plus 3 by 5 by S plus 5. Fine. I mean, that's, what it comes to numerically. So now, I mean, if I take the Laplace inverse, if I want the time response rather, what would I do? I would take the Laplace inverse of this, right? So that boils down to 2 by 5 plus 3 by 5 e to the power of minus 5t. Fine. So this portion, of course, mechanically, the calculation you had learned in your, system theory earlier in the second years, and you will be able to somehow obtain the response, right? So fine. That much is understood. Now, what we are going to strive to do over here in this particular class is that we would try to have a closer look at the response and see which part of it comes from where, right? So say, for example, I have the first part of my, the overall response, that is CT, consists of two parts. As I said, one constant part plus another exponentially decaying part, right? So where does each of these parts come from? So that is what we are going to look at. So the first part, that is 2 by 5, actually came from this 2 by 5 bias that I had broken up the overall thing into these two partial fractions, and this is from where the first part came. Now this is along with 2 by 5 into 1 by S. So 1 by S actually came from where? It came from the input which was applied to the system. What I mean to say is that because the step input is applied, basically this portion led to this constant part coming. So this is the forced response. What I mean over here, you can further understand by, if I say that if instead of a step over here, I apply a ramp input, which part is likely to change, or which part will be changing in my overall response? I will see that if I apply a ramp input, basically what will happen is, you will, of course, again, you will take the 1 by S square over there, and then you will break it up again into two parts like this. So the first part will be some constant by S square, and that will lead to some constant into T, right? So the first portion and then another exponentially decaying part. So what it means is that if I apply a ramp input, I will have the forced part of my response is going to be different from what it is when a step has been applied, right? You can directly visualize that. You will see that 2 by 5 into t means it's going to follow a ramp now. Something constant into t means a ramp is the response, right? So basically, this is the forced portion of the response, which is actually due to the input which has been applied to the system. To emphasize, that's why I'm changing slides. The same slide is what I have over here. So now this portion, the second part now I'll look at. So the second part is actually some constant into e to the power of minus 5t. Now where does this e to the power of minus 5t come from? It actually comes from this s plus 5 in the denominator, which gives you e to the power of minus 5t. Now what is this? I mean, from where did this s plus 5 come? Actually, it came from the pole of the original system. So the pole of the original system, which was located at minus 5, gave me this, I mean, portion of the, after I broke it up into partial fractions. And finally, it led to the exponential portion, which is e to the power of minus 5t. So say, for example, if instead of in this, or I mean, in this transfer function, if instead of in the denominator, if instead of s plus 5, if I had s plus 10, then the pole location would have no longer been at minus 5, but it would have been at minus 10. And consequently, I mean, this also, this portion of this fraction is going to be s plus 10 over here, and it will lead to this being equal to e to the power of minus 10t, isn't it? So you can see that the pole location directly leads to the natural response, right? Now, I mean, I would like you to look at something else over here. Something else means that, say, here it is, the pole is located at minus 5, and consequently, I have e to the power of minus 5t over here. Fine. Now, let us say that I have over here, the pole location is at minus 10. So, because of that, now I will have, I'll get e to the power of minus 10t over here, right? So if I get e to the power of minus 10t compared to e to the power of minus 5t, what is the comparison? Meaning, which one is slower and which one is faster as far as the decay is concerned? As far as decay is concerned, it's an exponentially decaying function, right? E to the power of minus 5t. So if I have e to the power of minus 5t, and I mean, the case 2, say, I have e to the power of minus 10t because the pole has been shifted further and gone to minus 10 instead of minus 5. Then I will get e to the power of minus 10t. Now, comparing e to the power of minus 5t and e to the power of minus 10t, which one is decaying faster? That is the question.
minus 10.
Yes. So obviously, e to the power of minus 10t decays faster. Now, decaying faster means what? If I just do the plot, I hope you can see the cursor. In the case of e to the power of minus 5t, say, for example, if it decays somewhat like, cursor is disappearing, but I hope you can see it. It's decaying like this. In case of e to the power of minus 10t, it will be much sharper in the decay. As far as decay is concerned, the decay will be much sharper, isn't it? Because it is going to decay faster, right? So what happens is that the farther the pole goes away from the imaginary axis, the faster is the decay. So over here at least, right? So what it means is that poles which are close to the imaginary axis are called slow poles. Poles which are far away from the imaginary axis are called fast poles, right? Now, the effect of fast poles is that that portion of the response which comes directly from the fast poles is going to decay much faster, meaning that the effect on the overall response will be there for a much smaller period of time compared to if I had a slow pole where the decay is much slower. So the effect of that pole will be persisting for a longer period of time. So it means that slow poles have a much greater effect on the system response compared to fast poles. Fast poles means poles which have a higher numerical value, negative value is what I'm speaking of for stable systems, which have a higher numerical value, but consequently the effect on the overall response it is much lesser compared to slow poles which have a numerical value which is smaller, but that means that the effect will persist for effect of that I mean pole you can say is going to persist for a longer portion of the time, right? So all that is of course not written on this slide, but we will come to it by and by. So that's why I just wanted to tell you these things, because we will actually after some time we'll be considering the effect of what we call dominant poles of a system. Dominant poles means poles which would be expected to have much I mean higher effect on the system response compared to insignificant poles, as we call them. Insignificant poles are fast poles which decay fast, meaning that the effect on the response is very small. In many cases it will be such that you will see that basically insignificant poles are as good as neglected. We neglect, we say okay fine, I mean there's a pole at which is much which is much shifted away from the imaginary axis and it has negligible effect on the system response, let us neglect it. So such sorts of simplifications again are done because, as I told you, I mean computational effort is sort of very costly. So naturally people want to simplify systems, and by simplification we mean that say those portions of the system dynamics which have negligible effect on the overall response are sort of neglected compared to the other portions which have significant effect on the response. So in order to simplify systems, basically insignificant poles are often neglected. Now let us see what is written on this slide. Okay, a pole of the transfer function generates the form of the natural response that we've already seen. So this is of course the natural response, the second portion. Now, a pole on the real axis, as in this case, one single pole on the real axis leads to an exponential term, obviously, because one single pole would be, I mean, leading to something by, I mean, s plus that value, say p or something, in this case 5, and consequently, we will be getting an exponential term like this, e to the power minus something t. Now, the further to the left a pole is on the negative axis, the faster the exponential transient response will decay to zero. So this is the part that I tried to verbally explain so far, meaning that the larger the value of the pole over here, numerical value of the pole over here, the lesser the effect on the response, or rather the transient portion of the response will be persisting for a much lesser period of time. It will be very fast to I mean fast in its response, and then ultimately I mean say after some time the effect of such I mean a pole which is shifted away from the imaginary axis, it has a large value, the effect will be negligible on the overall system response. Only the effect of slow poles will be persisting, but in this case we have studied with only one pole over here, so that's why we are saying that this pole over here leads to this. If this pole is close to the imaginary axis, as in this case, you will have this response persisting for a larger period of time, meaning we will see an exponentially decaying portion of the response contributed to by this portion. Then you of course sum up with the other, and then whatever response you get, you will get. On the other hand, if the value is large over here, the decay will be faster. Next, we come to the constant, right? So when we broke up into partial fractions, we landed up with such values as 2 by 5, 3 by 5 and all that. Now, where do these values come from? Are they stray, or do they actually come from some portion of the system dynamics itself, right? So yes, it does come from somewhere. Where does it come from? It comes from the 0. So you can see you had s plus 2 over there, and because of that, I mean this 0 was located at minus 2. So from here basically, I mean, depending on that value, you can see that whatever you have in the numerator, depending on that, you will get these constants, right? So if instead of s plus 2 I had s plus 20 or something else, so naturally these values would have been different. On the other hand, I mean, just changing the zero location would have had no effect on number one, the I mean the nature of the forced response. The forced response would still be, because I mean if this say s plus, instead of s plus 2 I had s plus 20, right? So what will happen? This constant over here will be changing, this constant over here will be changing. So we'll have some other constant, k1 by s plus k2 by s plus 5. So what has happened? Something by s, that form remains the same. So forced response remains the same, only the constant value will be changing, right? On the I mean nature of the forced response remains the same. On the other hand, as far as the natural response is concerned, in the denominator we still have s plus 5, so k2 by s plus 5. So again, this e to the power of minus 5t will be remaining intact if, what I said is, if only the zero location is changed. So the natural response and the forced response, both natures will be remaining exactly the same, even if the zero location is changed. However, what will change? The value over here. Value means the amplitude will be changing. So amplitude of this portion, you can see it is a constant, means what? If I plot it on the time axis, what will be the nature of this forced portion of the response? It is going to look like a step, isn't it? Step function. So this is going to still remain a step, while the amplitude of the step will definitely be different. If this is k1, the amplitude will be k1. And also this second portion as well, the exponentially decaying function will remain exactly the same. On the other hand, the constant value, I mean, from where it starts decaying, will naturally be changing. And of course, the amplitude, that is, and of course, the overall response will be a summation of both of those responses. So what will be changing in the response if a zero location is changed? Nature of the response will be remaining the same. The amplitude will become different if the zero location is changed, right? So the zero helps generate the amplitude for both the steady state and transient portion of the response. So now some terms which you are already familiar with, that is first order system specifications, system response specifications. So for us, I mean for a system which is a first order system given by A by S plus A, that is the system, right, transfer function. And we've applied a step input of unit amplitude. So for a unit step input, you have unit step input means Rs is equal to 1 by S. So that Cs, that is the response, in the Laplace domain becomes equal to A by S into S plus A. Consequently, of course, if you take the time response by taking the Laplace inverse, you will, of course, the steps, meaning break it up into partial fractions and then take the Laplace inverse, you will get the time response like this. That's 1 minus e to the power of minus 80. So over here again, you can see this 1 actually comes from the fact that I had a step being applied. If it were not a step, that portion would have changed. Just repeating things that I already said. Also, I see that e to the power of minus 80, this a actually comes from the location of the pole over here, right? Now, coming to the specifications as we promised. So the time constant. So time constant is actually over here. From here, if we try to define time constant, or rather try to see what is the time constant in this system, 1 by A is called the time constant of the system. And of course, it is the time at which the response value is equal to 0.63. This, I mean, calculation you have done in your second years, and it's also shown over here. So CT, I mean, at t equal to 1 by A, if you calculate how much it is going to be, you can see it's going to be 3%. Now, time constant is the time it takes for the step response to rise to 63% of its final value. Final value or steady state value is what we say. Now, the reciprocal of the time constant is called exponential frequency. So this is something I guess you still do not know or did not study in your second years, may not have studied in your second years. The the reciprocal of the time constant is called the exponential frequency. So reciprocal of the time constant means what? We've said that time constant is equal to 1 by A. So reciprocal of time constant means A. So A in this transfer function means a by s plus a is the transfer function that we are speaking of. There, a is known as the exponential frequency. Why a is known as the exponential frequency? For obvious reasons, because in your response, you have this e to the power of minus 80, and that a is going to dictate the rate at which your exponential term decays, right? So a is known as the exponential frequency, and it's the reciprocal of the time constant. And it is related to the speed at which the system responds to a step input. So, I mean, as we already have mentioned, if a has a larger value, you have the decay being faster. If a has a smaller value, the decay being slower. So, the speed at which the system responds to a step input is related to the value of a over here. Now, a, that is 1 by time constant, is the initial slope of the time response curve. This you must have studied in your second year. So, I mean, if I have the response of the first order system, say for example, over here a numerical value has been taken just to obtain a MATLAB plot. So, you can see 1 by your 0.1s plus 1, which means that the transfer function is, you can say it in this form, and you can also say 10 by s plus 10, right? So, that is the transfer function that we put over here. For that, the plot has been done, shown by the blue, blue curve over here, and we can see that if you, draw the your slope at the or tangent to the initial portion of the plot, you will be able to see that it cuts your steady state value at a particular point. From there, if you drop a perpendicular, you will see that this from the t equal to 0 to that point, basically in time, that time is going to be defined as the time constant, which is 1 by a. So basically over here with the numerical values for a particular transfer function, it has been just shown over here. Shown means, you can see that for this, basically this has been done. So okay, so this value is 0.63, as you can see, on the plot. If this is the time constant, if you just project it, this is 0.63 of the steady state value, which is equal to 1, and this of course is the time constant. These are things, this last portion you are already familiar with, so I sort of hurried through it, but maybe 1 or 2 extra things I've said compared to what you had already known. Sorry. Now, continuing with first order system response specifications, rise time, you're familiar with this term. So, time for the response to go from 10% to 90% of its final or steady state value. So, time to go from 0.1 to 0.9 of its final value, same thing. And now, of course, if you actually obtain, say, the response CT in this form, and then you try to put in 0.1 and 0.9 over there in this side and try to solve for the corresponding times at which these occur, and then take the difference, you will be getting the value of the rise time in terms of the parameter of the system, which is A, right? So I think these derivations have been done explicitly in your second years. If not, you can go through any basic book on control systems. As I said, I'm sure you've understood what I've said, right? So you put 0.1 over here, try to solve for time, 0.9 over here, try to solve for time, and then take the difference of the 2 times, you will get your rise time. And that happens to be what is shown over here. Right? So for a second order system, it will be 2.2 by A. I am actually repeating these because in some of our problems, as well as when you do the response for different systems that we are going to study, you will be requiring to calculate, say, the rise time, the peak time, settling time, and so on. So that is why I am again putting the definitions in front of you, just as a recapitulation, mostly. If you are already familiar with it, maybe some minor points being added. Next, the specification, which is known as settling time. So the time for the response to reach to 2% of its final value is the settling time. Again, if you put in the value over here, 0.98, 2% means what? It's going to be 98 percent of the steady state value. So if you put in that on this side and then try to solve for time, you will get the settling time. It's being calculated over here, right? So in this particular plot that you see, basically for the specific system that is 10 by s plus 10, g is equal to 10 by s plus 10, some of the values have been shown by, actually plotting in MATLAB and then just putting the values over here at specific points. You can just go through it when you, in fact, I've given you the slides. So over there in your slide, you can just see. So for example, say wherever you can see where the amplitude is 0.63. So that will give you your time constant value over here, right? Similarly, rise time, you can actually see where it is 10% and where it is 90%, and then see the difference and then calculate the rise time from the plot, and that will give you the value, right? Similarly, the settling time. So you can see this is the point from which the settling time has been directly obtained from the plot as 0.391, approximately equal to 0.4, which is the calculated value over here, because A for us is equal to 10, right? Because as I said, this is 1 by 0.1 s plus 1, meaning 10 by s plus 10. So settling time, again, calculated value, you can see from the plot. Just for verification, nothing else. Sure. Okay, so let me do a bit of this as well, because again, it's going to be mostly a recap, but again, some points being added. So here now we are till so far we were looking at the first order system, apart from the general some definitions that we did. So now we look at the second order system response. So second order general transfer function, transfer function of a general second order system is given over here, b by s square plus as plus b, and an input has been shown over here as rs, and the response is cs. So now let us see what happens if a step input of unit amplitude is applied to it. What is the response and how to interpret it? Some of the interpretations thereof, that is. So the input pole, as I said, your input is equal to, it's a step input, so rs is equal to 1 by s. So basically input is a pole at the origin, but not the same pole that you, it's not the same domain in which you plot your system poles. It's a different plot altogether, but nevertheless, there's a single pole at the origin, which is the input pole at the origin. That will generate the constant or forced portion of the response. So basically, if you have one input pole at the origin as the as your forcing function, as we call it, or the input, basically that is going to dictate what is going to be your forced response. The nature of the forced response you will understand. So that will be obtained from the input pole at the origin. Now, apart from that, the system has its own dynamics. So the natural response will be generated by the dynamics of the system. So each of the two system poles, since this is a second order system, naturally how many poles are there? There are two poles of the system, and those two poles will be generating the natural response. Now, as you are familiar, when we speak of second order systems, the damping is very important, meaning that the nature of the response actually depends on the nature, the value of the damping ratio of the system. So we have what we call overdamped systems, underdamped systems, undamped systems, okay, critically damped systems, and so on. So basically, you are familiar with those terms as well. So here now, again, I'm going to just do a bit of can I continue with this? Meaning, do you have a class after this? Because it's going to be quite a bit after this. পরে কি ক্লাস আছে তোমাদের?
No, ma'am.
আছে? হ্যাঁ
No, ma'am.
বললেন?
We have.
You have. Acha, so I'll be doing this in the next class because
After
okay, so I'll do this in the next class because I mean I'll require quite some time, at least half an hour after this to uh, complete this, because second order you would have to look at in very detailed form. So I'll just stop the presentation, take your attendance, and leave you for today. Let me.
ম্যাম হাফ অ্যান আওয়ার হলে টাইম আছে
আছে আচ্ছা তাহলে তো ঠিক আছে. Okay, so I'll just continue. Now, fine. So first of all, an overdamped system, right? So overdamped system means what? Okay, so the transfer function that we've taken over here, you can see 9 by s square plus 9s plus 9. So what does that mean? This is in the general form of omega n square by s square plus 2 zeta omega n s plus omega n square. So how much is omega n? It is equal to root over of 9, which is equal to 3, right? And how much is the damping ratio over here? Your omega n is equal to 3, right? So how much is the damping ratio?
Can you repeat the question?
How much is the damping ratio for this system? Omega n is equal to 3, you can see that, because omega n
9 by
square is
6.
9 by 6, which is definitely greater than 1. So naturally, it's an overdamped system that we've taken over here, right? So now, first of all, looking at certain things which you are familiar with, adding on to that, as I said. So if I apply a unit step as the input. So for unit step input, of course, I have to, first of all, what will be done? Okay, so first of all, what is done is over here, the poles are plotted on the, it's mapped on the S-plane, right? So we see that for an overdamped system, the two poles, both the poles are on the negative real axis, right? And also we find that both the poles are, I mean, differently located, meaning they are not coincidental in nature. They don't fall in the same place. They have different locations on the negative real axis, right? That is typical of the overdamped system. Numerically or mathematically also you can understand that, because we can actually, if it's an overdamped system, we can factorize this into two terms, one of which is going to give you the location of one pole and the other going to give you the other pole. So naturally, for an overdamped system, both the poles are going to be on the negative real axis and they are going to have different locations, right? Now, I mean, because of that, what will happen? Now, let us say, okay, so if this is the transfer function 9 by s plus 7.854 into s plus 1.146. That is after the factorization. So if I apply a step input, the 1 by s also comes in. So cs is equal to this. So if I take the Laplace inverse now, I will get, you can see, three parts like this. What are the three parts? The first part you can see it just comes from the 1 by s over there. So it's a constant. Over here, 1 value. The next part is actually, you can see it's the first order pole that we have, the first one over here. So it's going to give you an exponential term, right, like this one. And then the second term also is a first order pole. So first order poles means again you'll get a exponential term, an exponential term. So basically the overall response consists of the forced response, which is this one, the first term, and the natural portion of the response, which consists of two exponential terms. Now, of those exponential terms, again, what can we see? We can see that this exponent over here, minus 7.854, is actually the location of one of the poles, whereas the other exponent is the location of the other pole. Minus 1.146 is the location of the other pole. So now, I mean, if I say, for example, this pole is shifted to, by designing somehow, if I shift it, say, away from the imaginary axis or near to the imaginary axis, I can exactly say whether the effect is going to be more or less. You can see that. I mean, one pole at a time, if I shift, I'll be able to visualize whether, I mean, how much the effect of that pole is going to be, whether the effect of that pole is going to increase on the overall response or it's going to decrease on the overall response, if I break it up like that, right? So, of course, the overall plot is going to be a summation of the three, meaning a constant, and then two exponentials added algebraically together because of this sign over here. So ultimately leading to an exponential like response like this, which is of course the response that we get for an overtime system. You are familiar with that. So the general form of the time response in case of an overdamped system will be a constant plus, as I said, two exponentially decaying terms separated like this with their respective constants. So k2 into e to the power of minus alpha 1 t, where minus alpha 1 is the location of one of the poles, and plus k to the k3 e to the power of minus alpha 2 t, where alpha 2 is the location of the other pole. So to sum it up, alpha 1 and alpha 2 will be the location of the two poles. K2, K3, of course, will be, will have to be calculated. The constant values are going to come from if there are zeros or not, depending on that, these values will be coming in. So values, of course, have been generalized and put over there, but the nature of the response will be definitely having this form. So the form will be remaining the same for an overdamped system. So similarly now for an underdamped system, if you the example that is taken over here is the same example, but the damping ratio is different, as you can see. So omega n square by s square plus zeta omega n s plus omega n square. So omega n is equal to 3 again, you can see. So how much is the damping ratio? 2 into zeta into omega n is equal to 3. So how much is the damping ratio?
Half.
0.5, right? So you can see it's an underdamped system. So in case of such an underdamped system now, what are the pole locations? So you can see that over here in this case, it cannot be broken up. It cannot be factorized, into real, parts. So basically what we will get is if you, try to factorize it, you will get a pair of complex conjugate poles given by minus alpha plus minus j beta form. And in this case, if you write the values, it's going to be like this. That is, it's going to be located at, the pole pair is going to be located at minus 1.5 plus minus j 2.598, right? So now, to generalize it, if you have an underdamped system, it means you are going to get a pair of complex conjugate poles, right? So far, of course, you already knew, nothing new in what I have stated. Now, let us see the time response. Time response form will be like this. So, if I apply a step at the input, then I'll have a constant that is, in this case, 1 minus, here I have another constant that is 1.155 e to the power of minus 1.5 t into cos of something. So you can see that. So now to sum it up, first of all, I can see in the response, I have a forced portion, that is this constant portion. Because I have applied the step, this is here. If I would have applied a ramp, I would have got something into t over here. This would have changed, right? The other portions mostly remaining the same apart from the constants. Now, constants meaning the amplitudes, right. Right. The second part of the response, that is this one, is the natural portion of the response, right? So the natural response is over here. Now, in the natural response, what do we see? We see certain things over here, right? One is that this last portion, cos of something, etc., etc., this portion I can call as a sinusoidally varying quantity, right? It's a sinusoidal term in general, right? Now, as far as the sinusoid is concerned, what is the amplitude of the sinusoid? I find that the amplitude of the sinusoid is what comes before the cos, that is this portion. Now, what is special about that? I find that there is a constant, 1.155 or whatever, e to the power of minus 1.5 t. So basically, the amplitude of the sinusoidal term is by itself an exponentially decaying term, right? I'll repeat that. There is a sinusoid. The second part, that is the natural response, consists of a sinusoidally varying quantity, the amplitude of which is an exponentially decaying term. Is that okay? Now, coming to the which portion comes from where? Now, as far as the sinusoidally varying quantity is concerned, I find that this is what the frequency, isn't it? So this frequency of the sinusoidal term, 2.598 in this case, comes from where? It comes from the imaginary portion of the complex conjugate pole pair. Is it not? So, if now if I say that keeping other things the same as far as my system is concerned and the pole locations are concerned, if I shift the the pole pair away from the real axis, meaning I keep it at minus 1.5 plus minus j. Now let us say I've put it at j plus minus j20. I've shifted it away from the real axis, both the poles, of course, the pole pair, keeping the real part the same. So which portion of my my response will be affected? This, that is the frequency of the sinusoidal term, is what will be affected. I will have, as I said, if I put it at plus minus j20, I will have 20t over here, minus some phase, whatever is there, right? So basically, what would that mean? The frequency of the sinusoid will be increasing if I shift away the complex part far away from the real axis. The complex part, the imaginary portion is larger. If the imaginary part value is larger, keeping the real part value the same in the complex conjugate pole pair, in that case, the frequency of the sinusoidal term will be larger. Similarly, if it is shifted near to the, only the imaginary part is going, if it has a smaller value, say if I have minus 1.5 plus minus j 0.5, 0.5, okay. So then I'll have only over here, I'll have 0.5t, which means that the frequency of the sinusoid is smaller. So that, sorry, you can see actually from the response. So if you shift away this complex conjugate pole pair away from the real axis, sinusoidal frequency increases. Increases means what you will get is over here, you will see that in your response, actually, you will see that there will be many more oscillations before it decays, right? On the other hand, if the imaginary part is shifted closer, the frequency is going to be lower, meaning that oscillations will be, number of oscillations will be decreasing before it decays, right? Now coming to what will happen if the real part is changed. So real part comes, I mean, affects what? It affects the exponentially decaying envelope of the sinusoid. So exponentially decaying envelope of the sinusoid means what? Basically, if say for example, instead of minus 1.5, if I have minus 15, I'm typically taking 10 times away because I mean, it can't be verbally and you understand it's going to be creating problems if I take difficult values or values which you cannot visualize. So let us say I shift it 10 times away. So basically it's at e to the power of minus 10t. So that the real part has just shifted away. The imaginary part still remains at plus minus j 2.598. So what will happen now? I'll have the the envelope, that is this one, will be now this some constant into e to the power of minus 15t. So what would it mean? It would mean that the envelope of the sinusoidal term is going to decay much faster. So what will happen?
You told that when we will shift that imaginary axis poles, then only the frequency will be affected. Then the transfer function would change, no? Then zeta would also.
Transformation will change, of course, it will change.
Then zeta will also change. Then all the values will get affected.
No, zeta, we do not want to change zeta. We are just going to, if you just take it, I mean, you take the imaginary part larger and then calculate the rest of it to keep, I mean, the other things the same. In that case, what will happen? That's what I'm saying.
Omega n or zeta, something would change to keep omega d constant. Then this amplitude also will affected.
No, amplitude will not be. Amplitude means your e to the power of minus 1.5. If I have the real part at minus 1.5, this value will be remaining the same. If you can
that value
that value will remain the same. So I mean here actually, I mean, if I'm taking the envelope is over here, you can see, I mean, it's I can have a better ছবি আছে পরে দাঁড়াও। The this is the envelope, okay. So the gray one. So the envelope, if it decays faster, you will see that it's going to be closing in much faster, like this, sharper. It's going to be decaying much sharper, and the sinusoid will actually, be capped by that. Capped means that, the amplitude of the sinusoid will be just touching that envelope at the two sides, like that. Huh. On the other hand, that's going to happen when? That's going to happen only when the real part is changed. It is increased means the envelope becomes sharp, the decay of the envelope becomes sharper. On the other hand, if I change the imaginary portion only, keeping the real part the same, then what will happen is that the frequency of this, meaning that you will have many more oscillations over here. Apparently, the envelope over here will be remaining the same, but many more oscillations because the frequency is going to
Ma'am,
increase.
suppose we are changing the omega d of the system. So, omega d, we
Omega,
know.
we are changing omega, your
Damn.
this,
Yes,
that is
yes,
your plus minus j, that is the imaginary portion only we are
yes.
changing.
So that is the j omega d we represent as.
Mm-hmm.
So
Yes.
we also know that omega d equals to that omega n into root over 1 minus zeta square. So omega n or zeta, anything should change if we change the omega d.
Omega n is changing, yes,
And then
naturally,
this
because
one.
omega n is changing, that is why your frequency is changing, of course, yes. Damping is
Okay, okay.
damping
Then
is not changing. Omega n is definitely changing, yes.
okay.
You are correct. Omega d is what we are interested in, and if omega d is changing, either omega n or omega d, as you said, yes, over here omega n is changing, isn't it? So that is why your frequency, as I said, is changing, and that is affecting this one.
And we know that zeta omega n is constant here, so zeta must be changing. That's why 1.1.
Who has told you that zeta
Zeta
is
omega n, zeta omega n is constant because 1.5 we are keeping the that means real at
no, no,
real
no,
pole.
no. I'll just give you another. We're supposed to do it the next day. Let me just show you. It's written explicitly somewhere, that's why. Just a moment. This one. Yes, so this figure will help you a bit. It was supposed to be done a bit later. You can see plus minus j omega d. You are perfectly correct in saying that. So omega d is actually changing if I shift these away, right? Now omega n is actually this one, whereas zeta omega n, this one is your real part only is minus zeta omega n, right? So if I keep your my real part constant, it means minus zeta omega n. Minus means of course negative. So zeta omega n together will remain constant. It will remain the same. Real part remaining the same means that. On the other hand, the omega d is shifting, means it's going to be omega d is changing. So omega d changing means that, naturally this omega n root over 1 minus zeta square overall is changing. From this figure, can you make out what I'm saying?
Yes, well, so if omega d is changing, then the theta is also changing.
Yes, it is changing.
So zeta is also changing.
Zeta is changing, yes.
So that amplitude will also change,
But
no? Because
zeta omega n together
yes,
will
yes, zeta
remain in
omega
the
n is
same.
constant. That and
That is constant. So that is
but
constant would mean that
that e
your
power
envelope
thing
will
is
remain in.
constant, but 1.155 thing that's constant.
1.155 Tabolini. That is different. That constant is different. I'm saying this your 1.5, this
Achha,
minus 1.5, that portion is what I'm speaking of.
okay,
Eta.
okay. Hmm.
It so happens যে দুটো ভ্যালু কাছাকাছি. This constant I'm not saying anything about. ঠিক
Okay,
আছে?
okay. Hmm.
This constant is coming from এখানে, if I had instead of 9 I could have had something else. That's not going to depend on my omega n value, not on my zeta value. I could have had, say, instead of 9 I could have had 20 over there in the numerator, I mean. So that would be, changing my 1.155 to some other value. That's a different issue. Okay. So this value I'm not saying anything about, but e to the power of minus 1.5t, that minus 1.5 will remain the same if your zeta omega n that means this real portion is same. It will remain the same. Is it clear?
Yes, ma'am. Yes, I was telling about the one constant part.
Constant term changing means what? Say for example, if I double this, what will happen? The nature will remain the same. এটা আরো মানে বড় হয়ে যাবে, but it's going to I mean, as far as the nature is concerned, amplitude will double, but the nature will remain the same. The constant only I'm speaking about. But the value over here changing means the nature will be different. Okay. So this constant over here, that is 1.155, actually accounts for only the amplitude. So whatever be that amplitude means that many times it will increase or decrease or whatever. And that actually this value comes from the numerator portion naturally. Okay. So that way, but I mean, as far as the nature of the response is concerned, it will still remain the same. Even if this portion, I mean, it doubles, the nature will remain the same. Nature remaining the same means, when I say that, I mean that, I mean, say how many cycles before the decay occurs, that will remain the same, meaning the frequency of oscillation will remain the same. And also the envelope, that is, I mean, how fast or how slow it decays, that will remain the same. So, okay. So in the general case, now general case has been just put over here, and finally connect. I think there's a just this bracket. I keep on forgetting to correct it. Just a moment. I'll just. It's a cosine term like this. Sorry. In general, the phase shift has been shown over here. If it's 0, it's 0. If it's there, it's there. So basically now, I mean, this is the general form. General form again, I mean, the constants as we've discussed. This, I mean, the constant values will be coming from whatever is in the numerator, as well as the amplitude of the step. If it is, say, for example, non-unity, again, these values, the constant values will be different. On the other hand, the envelope, exponentially decaying envelope, how fast or how slow it decays depends on the value of alpha. What is alpha? Alpha is the real part of the complex conjugate pole pair. This one is alpha. Similarly, cosine cos of beta t minus phi means that the frequency of the sinusoidal term is actually your beta. Beta means the imaginary portion of the complex conjugate pole pair. So, of course, these can be mathematically, you can see how much these are phase shift and the constant value, etc., etc. Those can be numerically done. But I mean, physically, which one depends on what is, I mean, what I've tried to give you an overview of. Similarly, now an undamped system, of course, you see the damping ratio is equal to 0. So 9 by s square plus 9 is what has been taken over here. You have a pole pair on the imaginary axis at plus minus J3, as you can see. The response over here in this particular case happens to be 1 minus cos 3t. Now, here in this response, again, what do we see? First of all, the forced portion of the response, because a step has been applied, you have this one over here. And as I said, if you say, for example, instead of a unit step input, if you apply a step of magnitude capital A or something, you will have capital A over there, and correspondingly over here also, the constant value will be different. But now, the other portion, that is this, that is the sinusoidally varying term. Now, what about it? Here we find that there is the frequency of the sinusoidally varying term actually comes from the location of the imaginary portion. So again, I'll repeat, if I shift this pole pair, say, far away from the real axis, means that the values are numerically becoming larger, means that this is going to have, say for example, if I shift it at 2 plus minus j9, so I'll have cos 90, which means that the frequency of the sinusoid is going to be becoming larger. Similarly, if I shift it closer, meaning the value becomes smaller, the frequency will be smaller. So it's going to be slower, right? Also now, in this case, what we find is that the sinusoidal term has an amplitude, but that amplitude is constant, isn't it? It's 1 over here. It could have been non-unity as well, depending on what I've applied as at the input and all that, the amplitude. But the amplitude is definitely constant. So now that would mean that the sinusoidal term is going to have undiminished amplitude. Undiminished means it's going to have a constant amplitude rather. It's neither going to, become smaller nor going to become larger. So constant amplitude sinusoids is what I get. And as I said, the imaginary portion, the value becoming larger or smaller will dictate the frequency of oscillation over here of the sinusoid, right? In the general, I can note it. Just a moment. Somewhere this typo cropped in, and each time I correct it, but I forget to save it. Let's see whether I save it today. Save it here itself. Just a moment. Okay. So you find that again in the general expression as well, you have a constant term plus some constant into the sinusoidal term. So in any case, the sinusoidal quantity has a constant amplitude, right? And that implies that we have the undamped response, which we already knew, of course, right? Saving, taking a bit time to save. Let's see. Next, of course, the critically damped case. So critically damped case, you can see omega n is equal to 3. So you have zeta is equal to 1. So now over here, the time response for this particular case is given. This is slightly, sort of different. The expression is a bit different, but here now for a critically damped system, we will again have the pole pair on the real axis, but here in this case, the two poles are coincident, meaning the location of the two poles are going to be the same, contrary to the overdamped case where we had the pole pair on the negative real axis, but they had different locations. In the critically damped case, both the poles are going to be located at the same location, in this case -3. So the response is shown over here, and response means the expression for the response, and you can see both are having -3, -3. And if this is plotted, it happens to be like this. So it's actually not exactly not exactly an exponential quantity, only a summation of these three is what we get over here. So in general, this is the expression for the critically damped case, where you have this e to the power of minus alpha t in these two cases. Alpha comes from the location of the pole pair, same poles, of course. So just to, I think, already short of time. So the general case, just I'll finish at this one maybe for today. So you see that this is what expresses the whole thing. So the pink one is the actual response when a step input is applied to an underdamped system, right? So underdamped system now, we would be seeing that the response would be oscillatory. It's sinusoidally decaying quantity. So now the sinusoidal oscillation is generated by the imaginary part of the complex conjugate pole pair. We've already seen that. So as if the imaginary part value increases, sinusoids and the number of oscillations over here will be increasing. If the value decreases, the number of oscillations will actually be decreasing. Also, if we keep, say, for example, the imaginary part the same, but the real part becomes larger, it means that this envelope will be sharper in decay. and if the if the real part becomes smaller, meaning the real part is such that the complex conjugate pole pair shifts closer to the imaginary axis, in that case the envelope will have a sort of slower rate of decay. Slower rate of decay means that you will have the the decaying, sinusoidally decaying quantity will be persisting for a longer period, meaning that actually I should not be saying persisting for a longer period. What I should be saying is that there will be, basically, uh, uh, more oscillations, but the frequency, of course, is not being affected. But before decaying out, the number of oscillations will be larger, meaning that what I say is, say, for example, it's going to have the same rate of this same frequency, but the rate of decay will be smaller, which means that it will again have 2 or 3 more cycles before it actually uh, damps out, right? So that is how the real and imaginary parts of a complex conjugate pole pair um, influences the response of a second order system. In this case, the underdamped system response is what we are speaking of, because that's the most general one. And in fact, we are speaking of the complex conjugate pole pair in this case. I think that would be. And I think I'll stop over there today. Okay. So we still have quite a few things after this. I'll take the attendance. Don't leave.